Let's go back in time for a minute and talk about that number e again. Recall we used e as the base of a problem where our interest was compounding continuously, meaning always compounding, which would be nice if it were real. E is an irrational number, and irrational numbers have decimal expansions that go on forever, just like pi or root 2. The value of e is approximately 2.71828, although you could be more or less accurate depending on what your needs are. The reason e is important is it usually shows up in the base of real-world scenarios. We'll see this as the base of both exponential and logarithmic functions. We looked at an interest problem, and that was a bit contrived. But the real model that shows up a ton is population modeling. Recall, that's when we looked at the world population clock. Population really does grow continuously. A baby is born now and now and now and now and now. They don't wait for the first of the quarter in order to reproduce. So population models are continuous. You could model those with a base of E. Half-life problems are another good one because radioactive material is always decaying. It does not wait for the first of the month either. So E shows up in these natural, real-world scenarios, so we tend to call them natural base functions when they show up as exponentials. We actually have an example natural base function. It was our A2070506 model for continuous interest. The parent function is just f of x equals e raised to the power of x. We'll look at transformations of those exponential functions when we start graphing. But for now, our parent model is just this one. And keep in mind, we have used a transformation of that model in the past, our A2070506. What's going to be new is base e for logarithmic functions. Keep in mind, every exponential function can be rewritten in log form. So if I can have e for the base of an exponential, I can have e for the base of a logarithm. So logarithmic functions with base e are called natural logarithms, usually called natural logs for short. And the parent function there is a log base e of x. Often that's just abbreviated ln. ln for natural log. Note that it's backwards. It's because we take the abbreviation from French. So if you look at your calculator, e and natural log are located in the left side, kind of towards the bottom. Waiting for the calculator to wake up. There we go. So second, your blue key, down here in the lower left, you see your exponential, e to the x, and you can raise e to any power you want. Let's do e to the 5. Again, you see kind of an ugly number. E to the first power, well, that's that 2.71828 that we were talking about earlier. If you don't hit the second key, that's your natural log button, ln. And again, you can evaluate ln at any number you want. So I can do ln of 12. I can do ln of anything in its domain. If you want to have a really good time, you can do ln of e. Keep in mind, those are inverses of one another. So ln of e would just be 1. ln is a logarithm, though. So you have to keep in mind you're not allowed to put 0 into it. That's a domain error. You also can't have negative values inside of a natural log. That will give you a non-real answer. So there are a few caveats to logs. You can't put anything you want in them. It's also worth noting that if you do alpha f2 and use your log base function like we did in the previous section, you can do log base e. It's a bit of extra work because you have to put a 1 in the exponent for the e spot. But if you do log base e of 5, that will be the same thing as just ln 5. So it is worth knowing the shortcut. Using ln as a shortcut does save us some time. And I will probably never type log base e into my calculator again. I will always go back to just ln. So brief intro on the vocab here. If any of this feels confusing, raise your hand. Let me know if you have some questions. Otherwise, we're going to start using some logarithmic properties along with this new notation. See you soon.